Welcome back. Today we're going to be going over asynchronous programming in Rust. I'll first cover the fundamentals of concurrent execution and how asynchronous programming is implemented in Rust, and then get into a coding demo using keywords like async await and describing features a little bit better. This may be a bit longer of a video, but it's pretty useful to understand what's going to be going on under the hood when you use async and await in your Rust code. If you're coming from something like JavaScript, futures on the surface are pretty much the same thing as promises, except of course they're implemented in pretty different ways. So let's jump right in. If you want to skip to the coding demo and get over all the abstract, scrub to the timestamp that I have provided in the video and in the description. Let's say we're building a really big web server that uses blocking I/O. For small scale applications, we would actually be fine if our thread's blocked while waiting for something like disk access or network access. But alas, I/O is where the majority of our thread is going to be spending time in a program that deals with networking or disk access. Or more accurately, I should say that our thread goes to sleep, but that's what concurrent execution tries to solve, is what to do with this dead time when the thread could be doing work when it is instead sleeping, waiting for something like disk access or network access. So think of it this way: on our super big web server, let's say we have two users. We have a user A and a user B, and they both want to update their cart at the same time. We could spawn a new thread for each user, and that would kind of solve our issue here of blocking for waiting for user A's request to complete and then moving on to user B's requests. But this gets expensive really quick, especially if we only have, say, a handful or so cores on our CPU, and we're trying to process thousands of requests at the same time on thousands of different threads. You'd run out of memory really quick if you tried to spawn a new thread for each request. In this case, it makes more sense to have one thread for each CPU core, and to take those users' requests into a queue and process them one at a time. So going back to our example with one thread where we're processing two requests and we batch user B's request after user A, we're going to go ahead and do user A's request first and then followed by user B on the queue. Makes sense at this point, right? This is where async programming comes into play. Instead of just sitting around during something like network access, let's say for this authenticate user A task right here, we have to go ahead and talk to some external like identity provider or something like that. That's where this I/O comes into play. That takes a lot of time. And then we go ahead and update the user A's cart. There would be more I/O here as well. When we're talking with our database, right? And the same thing with user B. So we first talk with some identity provider and authenticate our user, and then we update the cart, just as a high-level example. Instead of just waiting around while this is happening, we can do something like this, where we jump to our task B, or handling user B's request, while we're handling user A's request at the same time. So we could first go ahead and kick off user A's request and authenticate it with this with our, let's say, our identity provider. And while that's happening, we have dead time. Our CPU isn't doing anything, right? So we can go ahead and process user B's request while user A, we're still waiting for a request from our external identity provider for user A. And then once we get that back, we can do our user A cart update. And then while we're waiting for database access to update the user's cart or whatever we want to do, then we can go ahead and process the second part of user B's request. What we're essentially doing is just zippering this, right? We have this dead time and we're filling it with stuff that the CPU can do while the thread would otherwise be sleeping. Let's move on to something a little bit more tangible. Let's say we have an async block of code here, and in this diagram we are doing two network requests. We are making a request to foo1.com and foo2.com. On their own, the network requests aren't anything but futures. For now, think of futures as snapshots as to what our asynchronous statements are doing. These are both asynchronous statements, right? Both of these request functions here essentially say, since they're futures, these futures are saying, hey, I have some work to do, or I'm in the process of doing work. By themselves, they don't do anything unless we invoke them, like what we're doing with the this join function down here. We then begin the concurrent execution of the request through this join function here. Under the hood, each request will initiate a TCP handshake with the server it's trying to download data from. While waiting from foo1, foo2 begins its handshake, and once both sockets are connected and data starts coming in, we will switch from emptying foo1's network buffer and foo2's network buffer. This is getting pretty low level, but at the same time, it's probably a good idea to understand this. So that is, if foo1 is a slower connection, we won't sit around and wait for data to come in. We will instead be reading data that's coming in to our foo2 network buffer. Finally, when both requests are complete, we send the data back up the networking stack through our runtime layer, where we can actually use it in user-facing code, and that would end up being our data 1 and data 2 here. In a nutshell, what we've basically done is that instead of saying, okay, download everything from foo1.com and then download everything from foo2.com, we're basically saying download them at the same time, more or less. We'll fetch data or grab data from foo1 as it becomes available, and if there's nothing left from, like, let's say it's a slow connection to foo1, then we switch to grabbing data from foo2.com. That's kind of what we're doing in a nutshell. It's the same ideas over here where we have some blocking operation. We're just zippering it. We're doing this zipper operation where we're interleaving CPU bound tasks with IO bound tasks. So again, concurrent execution of both requests is a lot more powerful than waiting for just one request to completely finish, then wait for the next one. I'll just say it again, that it allows our CPU to do the same amount of work in less time by not sitting around and idling while we're waiting on IO operations, such as waiting for data to come across from the network, or maybe read from our disk drive or something of the sorts. We did just mention a runtime layer too. That would be this over here. Just bear with me as we get through this. I know this is a lot, but it is a really good idea to understand what's going on under the hood so that you're better or more aware of what the code you're writing actually does, right? So our runtimes act as our scheduling layer and tells the CPU which tasks run and how to wait for IO blocking tasks. It basically, our runtime basically is decides how to zipper together our tasks here. So if we're waiting for IO, the runtime might see that, hey, we have this authenticate user B task that is ready to go, and currently we're waiting for network access or communication, so we'll go ahead and run this while this is waiting. It's responsible for organizing how things are run. So we'll just start from the top down with this stack in terms of what our async programming quote unquote stack looks like. So at the very top, we have our business code, which is the code that you and me see when we write out a asynchronous code. So that would look something like this, where we have our requests, and I'll go ahead and just delete that right there. But basically, we have an async block code, and then we basically invoke again our futures with this await keyword here. It's not a method, actually. We don't have parentheses at the end. It's a keyword that invokes the future. And below that, we have futures. And when we compile our code, Rust actually creates an enum that describes the future's state. In our example, we'll keep it simple and say that again, there's only three futures. We have request 1 and request 2, request 1 and request 2, and then we said that our join is a future as well, right? So again, futures don't do anything by themselves until we call the await field on them, await, which is why these request 1 and request 2 don't do anything until we call wait on the future that's actually invoking them. So we kicked off our join future here with await, and Rust creates a state machine so we know where we left off in our execution if our thread decides to switch to something else. Inside of rec1 complete and rec2 complete, we would actually have mini states, because this would be the state if request 1 is complete, but request 2 would not be complete in this request 1 complete enum variant here, right? We would have something like this, where we're still pointing to, within this variant here, we're still pointing to the request 2 future, rec2 future. That would still be within this variant that we'd be able to hold. So we know the state of what our request 2 future is, and same thing here with request 1. We would have, or should I say request 2 complete, we would have a request 1 future that's keeping track of what's going on within request 1. And again, these futures, they're basically the state of what's going on. So this could be maybe like a user request future going on here, and we have step A, which would be authenticate user A, and then step B, which would be update user B cart, something of the sorts, right? Or maybe we have a update user cart future, and that's what this does. It's a little complicated, not gonna lie, but we typically don't need to be worrying about this too much unless we're actively developing a runtime. But it's good knowledge to know, to understand that, hey, we're basically creating these states for each future that we have, so that we know what is happening within our future when we decide to pause from it and switch back to it. So in a gist, Rust makes an enum based off of our futures, and again, to help our runtime keep track of what's currently being processed, which could be both requests in this case, or maybe one request is complete, or maybe both of them are complete, in terms of when we're looking at this join future right here, this join state future right here. We keep track of this state because we may want to switch to other work that can be done on this thread. So like, again, going back here, maybe this is our update user cart future, and we want to keep track of this because we might switch between our user A update cart future and then our user B update cart future. And then we need to figure out where we are in the future here. We could say when we come from authenticating user B and then switching back to the user A future. We've already seen that we've authenticated user A, so then we go on to update user A cart. Next up would be our runtime here. We've covered the business code, which is this, futures, which and again this gets made for us, this state machine, if you will, of hey, where are we in the future currently? And then finally, we kind of talked about this, but we're gonna go over it again. Is a runtime which actually manages this state. It basically helps us update this join state and switch between different futures in case, again, like over here, it might switch between the request 2 and 1 future if both are pending. If both are pending, now we're dealing with futures within a future, right? So we might have both pending here, both pending, in which case we have rec2 and rec1 futures within this variant of the state, and our runtime would be responsible for switching between the foo1 future, which would be this block here and this block here, and then also switching between that and the foo2 future, which would be these two blocks. Note that the Rust standard library doesn't have its own runtime, actually. That's because the Rust developers wanted to keep bloat in the standard library to a minimum and to allow different runtimes for different scenarios. For example, if we're writing an embedded program, it would be interfacing with the hardware directly instead of doing system calls. For this video, we will be using the TRPL runtime. That would be TRPL, the Rust programming language. That's where it comes from. Although there's others out there, most notably Tokyo is a pretty big standard for runtimes out there. And then finally, our runtime communicates with the kernel directly, or like we said, directly with the computer's hardware to help us figure out when an I/O operation is done and we're able to update the state of a future. For example, when data from a disk becomes available in a buffer, the kernel will notify our runtime up here about this, and then the runtime can then update our state here and move on to the next CPU bound task. So that's it for the abstract behind the async programming in Rust and how concurrent execution works in Rust. Hopefully that wasn't too complicated, but again, it's probably a good idea to understand this so that you feel a little bit more confident when it comes to writing async and await code. So let's get into some examples now. Went ahead and created a new project called Async tutorial, and we're going to go ahead and add the TRPL crate to our project so that we'll be able to use the async runtime that it provides. So we'll go ahead and do cargo add TRPL. Not too bad, good start. And we'll go ahead and write a web scraper. That's what we're going to do. So what we're going to do with this web scraper is just pull the title off of websites of our choosing. So we'll first bring the HTML module into scope from TRPL. We're going to use that from the TRPL crate as well. So use TRPL HTML. And then we're going to create async. So anytime that we want to make a function that uses await keywords in it, we need to first declare async function page title, and this is going to take in a URL that is a string slice, and we're going to return an option of string, so we might get a title back, and we're going to first fetch to the web page. So response is going to be trpl get URL, and then we're going to, this is a future here, so we're going to go ahead and wait for this response, and this just kicks off the response. To actually get the full HTML body from the response, we need to call the text method on our response. So we're going to say let response text equal response dot text, and this is a future as well, so we're going to await that. And then the rest is non-asynchronous. This is all CPU bound stuff. We don't have to wait for IO. So we're going to go ahead and do HTML parse, and we're going to parse our response text. And then we're going to select, this is again just some the methods that are available on this crate. So we're going to go ahead and get the first item, as we can see from the document, and we're going to get the title tag. So we're going to get the first instance of a title tag, and then we're going to, that's going to be an option, and option provides this handy dandy map method on it. So in the case that we do have some value, we're going to get the title, and we're just going to get the inner HTML from that title. Otherwise, we're going to return none. So these get and text methods are, this is a function actually, and this is a method, are IO operations, which indeed make these statements futures, and we can invoke await on them like we just said. We use the parse function to extract out the title tag, then get its data. Note that we marked our function async as well. This doesn't truly make the function itself async. Instead, it gets transformed into something like this. So again, our function gets transposed into this before it gets compiled. Note that again, our function is marked as async, but that doesn't make the function itself async. Instead, it makes the body of our function async, which in turn turns this block of code here into a future itself. And that future will have a state associated with before and during and after the two children futures in our scope with the get and the text. We just chain these together. That's all we did here. In other words, we have a state every time control is handed to the runtime with the await. When we await something, we hand control over to the runtime. And again, our parent future, or the future that we define with the async keyword, will have the associated states once it's compiled. So just like how we went over here, that we have this state machine that's set up when we create a future, we do the same thing here. So it's going to look something like this internally. And again, we never see this code, but Rust makes this every time that we create a future. So we're going to have this page title future, and we're going to have initial, which would be like up here, initial, and then get a wait point. And I'll just actually make this like so that's a bit easier to read. So we have initial, and then we have our get await point here. And then we have our text await point here. And this is just letting Rust know where to pick up once we, if in case we switch to some other task. Also note that we're still outputting an option of type string down here from our future, which lines up with our associated output type. And again, we're implementing, this is a future here, and our output type for the future is going to be an option of type string. So just as a quick recap, we created an async function which gets transposed into this declaration here, and we went ahead and we have an async block here, and in turn Rust has this internal state machine set up that keeps track of where we are in our future every time that we await, and it keeps track of the variables that are associated with the futures as well. So for get await, we have a URL, and it keeps track of that, and it keeps track of our response as well for the text await point. I'll go ahead and just clean this up real quick. Now, if we tried calling our page title from main, that's not going to work. We could try doing http foo.com, or we could do some like google.com. This isn't going to work because main itself, like we just described, isn't a runtime. It's not a runtime. Since Rust does not implement a standard runtime for main, instead we need to create a runtime in which our async code can run, which in turn, again, acts as our scheduler and is in turn able to do all the fancy scheduling stuff that we have described here. We're able to pause a future and work on a different future, and then go back and work on the existing future based on our state machine here. That's the job of the runtime. And that's why we have also imported or brought into scope the TRPL crate. So we're going to create a runtime in which our async code can run, and we can do so by using the TRPL's block on function, which blocks execution in our current thread until all the futures within the block complete. That would look something like this. So we could have TRPL block on, and then we're going to give it a future, and within our future we're going to match our page title given a string of, we can say, let's do google.com, and then we're going to await it, and then if we get a title, we're going to print out the title. Otherwise, no title. So let's go ahead and try this out. As you can see, we finally got some asynchronous code running on our machine. We got the title Google for google.com. Now, at this point, nothing particularly special is happening. We're still effectively running a sequential program because all we're doing is waiting for this and then waiting for that. It's still blocking. In other words, we're awaiting the for response text, which in turn waits for a response from the URL. This, again, acts pretty similar as if we just had code that blocked during I/O access. What makes async programming pretty cool is that now we can have the ability to do concurrent tasks. That is, we can switch from task A to task B and vice versa when the other task is blocked waiting on I/O. Again, we're going to be doing something kind of like this, where maybe our user A future is blocked, and then we can work on user B in the meantime. We're going to do something more like this right here, where we're going to scrape two websites, but instead of joining them, we're going to select the first one that completes, and then discard the pending future, the pending request to, or the pending web scrape to the website that has not finished downloading yet. That could look something like this, where we go ahead and we set up two futures, one for google.com and one for the Rust language official website. We went ahead and let them race against each other with this select function right here, and we invoked them. We invoked this race future with await, which in turn invokes these two futures here, and then we pulled out the HTML title from the winning future. So this either type here allows us to select one of the two futures here. So if the left future won, then we go ahead and extract it, and if the right one, which is future 2, wins, then we go ahead and extract that. So I'll go ahead and run this one more time. I ran it just to make sure it works, but let's see what wins, Google or Rust language. Yeah, Rust wins. So Rust returns before Google in this case. If we had like a slower website, then in this case, Google is the slower website of the two. That's a lot for one video, so let's take a break here. In summary, we've gone over how asynchronous programming works in Rust from the business code all the way down to future generation, and down to how the runtime handles futures, and how the runtime interacts with your operating system's kernel or directly with the hardware. We have also seen why futures are useful in that they're able to run two futures concurrently and avoid blocking our thread with timely I/O operations. We saw that in an example of a diagram here, and then we saw it in action when we raced between the two futures and saw which one downloaded first. These two were running concurrently. That is, the runtime was switching between the two until one of them downloaded first. We didn't wait for Google to download and then wait for Rustling to download. We ran them concurrently. And yeah, that's a lot, but feel free to scrub back to different points in this video that you might have found confusing. I'm going to leave off exercises in this one, but yeah, hope you learned a lot, and I'll see you in the next one.